Hi everyone, this is Dr. David Jacob again for Science Education Innovations, and today we are going to talk about the practical applications of curriculum design, how to do backwards planning, which is really the work that we're going to look at. I'm going to start with things. Curriculum for the new science standards is better than you think it should be. Phenomenon-based, making pedagogical unit and lesson design, and formative assessments everywhere to determine how well students are meeting those learnings and adjustments that you may need to make to them in order for that to work. So, the other warnings is try not to do this together. Work. There may be times that you do have to work because that's the nature of that you either on the friend or a friend in real life to work on it. Divide and conquer. Let's split this up. Do overall design and then start up into little places. It's really challenging to come up with a big plan, but you need to be able to try to do that and then it amongst you. And accept critique. This is the hardest thing. We have all masters of our classroom time, but now what you want to do is open your eyes to some critique things may be able to give you, and as well, and always look for new ways to be able to present it. So, iterative engineering does curriculum. So we don't typically think of curriculum engineering. I will absolutely argue it is every single day because what you want to do is be able to make real world connections for relevant to students' lives and modern world. So always work on with all of those elements at the same time. Where do I start? So you have to rethink about what you have done before in your classroom. So instead of just saying, same stuff every day, you really have to go, is this classroom am I in this classroom having the kids do a science and engineering or science and engineering practice in every single lesson? Are my students using a cross-cutting concept for sense making or multiple cross-cutting concepts for sense making as well? And are my students leaving the classroom today with just content or a disciplinary core idea? And I raise that up to the higher because sometimes when we're thinking about our content, what do we small ideas that really don't make sense in the real world? So we want to make sure that it's relevant and we make those real world connections. And those disciplinary core ideas, the DCIs, are really the bigger idea that we're working for. So you may want to reuse old activities but with a new purpose. So the task itself may be valuable, but what you're asking students to do might be different. You may word differently because of what performance, because of what the or practice, or the goal of the cross-cutting concept. So does the activity address SEP or a cross-cutting concept element? We want to look at this as it says. So when we're talking about designing for an element, the little points on your standards are the things that are the elements. So it says here, construct a scientific explanation based on valid and reliable evidence. So that means that in our classroom, we should be is the evidence that you are using to construct an explanation valid and reliable? And is it obtained from a source, including the student's own experiment, some theory and laws that describe the natural world operate today as they do in the future? So is this phenomenon something that's unique, or is it something that's been happening forever, like condensation? Difference in there, and how do we know what that looks like, and is that a good assumption? Designing a task, you have to consider all of those elements, and in the actual questions that you're doing, do they actually show up? If we look at the concept of cause and effect and the cause and effect, it says phenomena may have more than cause, and some cause and effect can only be described using probability. So that may mean that we want students to not come up with the cause and effect, but a cause and effect relationship. Is there more than one cause and effect relationship? The more that they're entertaining more of these, they then have to look for the evidence that supports that. And in this element, we want to use means is what is the likelihood that again the next time with the same exact outcomes. So those are something we want to look at and be very specific about it. Time is precious. So sense making takes more time than lecture. If you were going to just give the bunch of kids a bunch of information over 4 days and then have a test on Friday, that is really easy to do. But unlikely that is happening. So what you want to look at is what we're doing really, really essential for them to understand. Look for new activities that are 3D. Look online, look on other curriculum that's out there, but be very, very careful. Find sure that you use your own brain, especially if you're using AI for any of this. Make sure that you pull out your standards and say, does this really ask them to do an element like I just went over? Your idea for curriculum standards is cut, keep, and redesign. Cut a lot of it. There's probably a lot of used to do that are not at that level or may be at another grade level. If you're at high school, it may be a middle school or an elementary level idea that you're trying to get across. You can still reuse it and maybe go back and review that idea, but that should be a quick review and get to your idea or your subject. So cutting things out, if your tasks may be perfect. They may be phenomenon based already, but are you asking the design phase as well? Develop more 3 prompts and specific prompts. When and why. What you're looking for is very often we used to say how many carbons are on that molecule. Who cares? Anyone can count them. That's not very important. What we're really looking for is a student to be able to say, how did this get formed? Or can a glucose molecule end up in multiple forms to create a polymer of glucose molecules? And what do we call that? So those are some of the things that you want to look at. So where do I start? Make sure you've identified all the standards that your state has identified for your course. In Even though we've all used the state's same standards, some of the states may have put some of the performance expectations in different courses. Maybe everything will go in one. Since there are a lot of states that do not do earth science, they may have combined earth science in a curriculum project that you want to work on. So you really need to know what it is that you're working on. So teacher designed, if you are going to design your own, you have to plan units and check to make sure that all of your PEs are included and make sure that you've addressed them fully. So that is a lot of work to make sure that you're getting all of that. If you're going to use a commercially designed curriculum, make sure that the units address all of your state standards because they may not have been written for your state. So for example, in New York State, we're not an NGSS state, we are a New York State Science Learning Standards. That means that any curriculum that is written for NGSS needs to be modified by the teacher in the classroom. So for example, this is the biology curriculum, New Visions, which is a New York City curriculum for these standards, and it actually got the PAs. There's actually some that are missing in the biology curriculum, even though I really like what this curriculum has to say. So organize your PEs into units. You may have opportunity for approach. Maybe not the way you always started. Maybe starting the way you always started is going to be part of the difficult that you have. There's lots of ways to approach all of these. So goal, don't discipline. It's not discipline mastery. You're not trying to make them a chemist. You are trying to get to scientific literacy. What does every American need to understand about chemistry or physics or life science? We are not just creating biologists or chemists or pharmacists. We are trying to create somebody that understands scientific literacy. Remember, we want our lawmakers to know that, we want our scientists to know it, and everyone that is going to pour something down the drain that they understand it. What is the application and generalizability of that versus content details? Check for your DCIs to make sure that what you're doing is right on target. So if we're looking once again at the bullet points or the elements of these, what is it that we're looking for in these? In New York State, so once again, I'm in New York State and we have course maps that are there. So for each one of the subjects, biology, it actually goes over the topic, the PE, and some of the elements that go through it. In New York State, they've also added some earth science and engineering to the biology. So you want to make sure that you do that accurately. So I'm going to go through this one standard and this PE and all of the elements that go with this PE. So I'm going to take a look at a middle school one. So the performance expectation that will probably take more than one lesson is to construct a scientific explanation based on evidence for the role of photosynthesis in the cycling of matter and flow of energy into and out of organisms. You probably have not seen it this way before. So we're talking about the role of photosynthesis. It is not a memorizing synthesis or all of the biochemical mechanisms. It says, look at the assessment boundary that I've put in purple. It does not include the mechanisms of photosynthesis. So this is, and you're stating a question, they are not going to ask for the biochemical mechanisms They are looking for how photosynthesis is the flow of energy. That coming down the not having somebody understand. I argue that it's the opposite. We're looking at the purpose of photosynthesis, not just of look like that are there is that plants, algae, and organisms use energy from light and they call it food to differentiate between just sugar production and how that is stored as food from carbon dioxide from the atmosphere and process of photosynthesis, which also is oxygen. These sugars can be used immediately or stored for growth, not just photosynthesis, but how is that in cycling and the flow of energy in organisms? That is the big idea, is what we've done before. This is why I chose photosynthesis for explanation. Reaction produce complex food molecules, sugars, require input. Again, in this reaction, carbon dioxide and to combine to form carbon-based organic molecules. So we're looking at what the goals of this PE designed for it. So photosynthesis is a process in which use the sun or other light source to convert CO2 to water to make a form of complex sugars and O2 it produces. Plants can use this food and for growth or stored for later use. So once again, when we're looking at this, we understand energy can be used now and later. So the rabbit holes that we go down is the biochemical processes. It's not assessed. You may do it in your classroom, especially if you're honors classroom and they're going to AP biology. You may want to talk about the biochemical, but you're not going to assess them. It might be detailed understand or idea. The types of energy, whether it's sent red light, those might be because you may want to do the idea of farming or indoor farm, mission to Mars and how to grow plants on another planet. Tigers and their structures, low chemical discussion, but do you have time? And you want to be able to look at honestly. What are the goals of this PE and how do I design for it? The science and engineering practice. Can students prove both this process when given information? So when given information, can they prove that does this thing? And what are some of the investments in your classroom to do that? Are there, can students argue from evidence or explanation of that information? Can students explain ins and outs of this familiar light source stance? So that'd be a good question. Out the sunlight to a chain, what happens? And that might be what you want students to look at. Data, can students use that data to support a claim about the output of photosynthesis? Here, I'm changing how we look at this. Can students design that synthesis work? In that, but those, what are your, so what are the questions that we want to look at? Cause and effect. What causes the effect of photosynthesis that we're looking at? And transfer. How does it drives the motion and or the cycling of matter? So matter and energy are there. What are the matter that we're working with to turn into glucose? Water that's there to produce both that glucose and oxygen as often. Really important. Less our unit or ideas typical lecture. How might you go about this? Gave you all this ideas. I'm going to go through this, but show students a video of a plant growing in light. Maybe it's a vegetable plant. Ask how does this plant grow and store energy? What are things that you might have? Ask students develop a model of the components that have relationship between those components. Video that model may be terrible, but maybe what you want to do is have them revise that model of photos in the course of a couple of lessons. Their first may not want them to have, but do they get an opportunity to write models over a couple of weeks? Next, develop how light much produced. You want to get to what is it producing? Is there a that allows for oxygen to, does any light work with that? Provide students with an info, once again, getting them reading in the science and show a step-by-step produce or use that as some examples of simple reactions. Have used the models to construct and how this process is happening. So it's not on there. How much you may want to use that claim about what's in focus. And finally, maybe another lesson may revise their models again and again, as I had said. So we want to think about what it looks like as a whole. So what are the teacher moves you do? What are some of the pedagogical choices you write into your lesson, but get students to discuss it out and assess whether they want to say, I've got to do this all in 3 days. You want to extend this. Don't just ask them questions and circulate often to be able to figure out what that they are doing in their classroom at any given time. Students to explain individually or get them to verbalize it and write or develop a model and talk about of really important for the students to be able to get to at any given moment. How do you buy in for students? Making, they don't know enough. That is the common phrase that I've heard from some students may know more and use the classroom. They may know information, but it may not. Get that information out that to have that conversation. Source of information. you talking at them is effective of all these. What I see and I remember as some of the other ways you can look at this. Informational from a text or an article, and get them to read it and annotate it and use it carefully. One of the things we've talked about state assessments, there's usually an infotext that goes with it. Is it accurate? Is it readable? Work, and maybe teach the students what they have, so that they DC it to themselves. Is it qualitative, quantitative data? Both of them are valuable, and you want to get students to know the difference between those two types of data. We tend to over rely on quantitative data, but qualitative. Use real sources. Don't make a. Try to use as much as possible. This is where AI can student choices, whether the class whole, and make them check that data as a source of that information. Teachers need to help students with the information in science. Reading in science is different in other subjects. It's more complicated. You may want to search this online or ask your elementary colleagues. When you actually go, I'm trying to understand what this is. What is my guiding question for this reading text? In the first sentence, that answer. Is there any in the second sentence that can help me do that? Being able to do that, do as much as you can. So, thanks for watching World Actions. I'll probably do a part 2 video because there may be some other things to work on. Okay, and enjoy the rest of your day.